Well, welcome to our case study webinar series. This is John Sankey. I'm an engineer for True Blue Technologies, a sales engineering firm that supports groundwater characterization and some remediation technologies from ASTIS, Tersus Environmental, TRS Group, NRX, and West Bay Instruments. So what you're part of right now, this is a series of case study presentations that really focus on the main topic of managing complex groundwater projects with high resolution site characterization. And in some talks, we also talk about ways to mediate these groundwater projects. But today we're pleased to have Dr. Todd Hallahan show how a basin and project manager can manage their well networks with something called surface electrical monitoring and temporal imaging. And by the end of this presentation, you'll be able to explain to your team what electrical hydrogeology means. So Todd's background. Todd is a professor and Sun Chair of Hydrogeology at the Oklahoma State University and serves as the Chief Technical Officer for ASTIS. As one of the recent NGWA McElhaney lecturers, Todd gave talks all over the world. So Todd, thank you for presenting this presentation and some of the case studies. You now have the lead.
Thanks, John. And I've got a managed conflict of interest. I'm a professor. I've got grad students and those sorts of things. And I'm Chief Technical Officer for ASTIS, which is a company that's developed out of the stuff that I developed. So here we go. And we're going to chat about a bunch of stuff, but we want to be respectful of your time. So we do these as rather short webinars. So give or take 20 minutes with some Q&A to follow. If you want to stick around after the end of 30 minutes and keep asking questions, we'll keep answering questions, but we're trying to be respectful of your time and things. It's all being recorded, so if you go, wow, that was fantastic, but I need somebody else to see it, it'll be up on the website. So, or if you want to watch it again, if there's something you didn't quite understand, or give us a call and we'll explain it. And then the main reason a lot of people are here is because we give away a gift card. So there's either Starbucks if you like coffee or Amazon if you don't. And we put that in some sort of magical device and it spits out a name somewhere at the end, and we tell you at the end of the week who got that. So onward and upward. So I'm an electrical hydrogeologist. So looking into the subsurface, I can look in a lot higher data density electrically than I can just using a well. And so when I think about a problem of flow or transport, I'm thinking about it as far as what it is in the ground as far as how conductive or resistive it is. And then if I'm thinking temporally, I'm thinking about whether that would make it more conductive or more resistive. And so when people ask me questions about their site, I ask them some somewhat strange questions back because I'm trying to convert what they're saying into what that would do electrically. But the nice part about it is you can get to high data density. So a single image in the subsurface, that's a couple thousand data points, so you get a kilopixel camera, and then you start taking pictures and looking around. And so this is a small gas station site example, and you're doing small gas station sites with the 22,000 data points. So when you start looking at sites of that data density, you see a lot more things going on. And so when you're targeting where you're going to biopsy the patient or put in your wells, you're doing that quite precisely based on seeing what's down there and going into a particular portion of the domain based on high data density. So standard groundwater monitoring. We got to talk about wells a little bit. And John Wilson from EPA ADA, now Scissortail Environmentally, said, you know, wells are holes in the ground that lie. I don't know if that was his original quote. I think he might have said somebody else told him that, but I do find it useful. And you get information out of them, but sometimes you're not so trustful about it. So quite useful. You could quickly measure a water level. You can grab a chemical sample or you can grab some microbes out of there, and you can watch whether things change over time. And here's sort of this is a USGS sitting by a well, and it's got water built up around there, not far from going over the lip of the top of the casing and into the well. So when you measure something in there, has the well degraded, has stuff flowed into the top, have different things happen. And so the usefulness kind of degrades over time because as you're getting different signals, not so sure that's good. And then if the signal stays the same, the water level stays absolutely the same, and you're going, was that the well or did the aquifer actually at this location not really change? And so there's that trust factor with wells that we sometimes acknowledge and we sometimes don't. In the problematic side, well, you just put a way to move contaminants around in the subsurface, that might also bring it in from the top. So that one we kind of accept because it's just the way it's going to be if you put one of these things in the ground. So we try to engineer around that. In terms of being difficult to abandon properly, the one I think about is you go out to a site with 100 wells and you go, yeah, I'm looking for well 22. And they go, yeah, we haven't seen that one for years. We think somebody drove that over when they were mowing or da-da-da. There's always a story, but they're missing a few of the wells. And so you go, well, now I know I've got a place that might be connecting things in the subsurface. I already know it's damaged because I can't find it, or at least it's buried. And so it gets kind of tricky. And so if you just walk away from a site with wells, that's a problem. You can't just walk away. The other thing about wells is that they're not that cheap. People think about them as a pretty cheap thing to do, and they go, well, I'm just going to install a couple of wells. Every time you do that, the estimate's not from me, but somebody else did the calculation. That runs about $125,000 per well of installation, getting it sorted out, and then coming back and sampling it, and eventually abandoning it in some proper way. So people don't think about that because it's sort of spread out over time. And they go, well, these things are cheap, I'm just going to put a few more in. But you got to think every time you're shoving a hole in the ground, that's a $100,000 thing you're doing. And it ends up being kind of low data density that you go, okay, well, I want to look at these spots. And you go, well, how many spots do you want to look at? And the data out there say, well, if you want to look in an aquifer pretty usefully, it's about 10,000 data spots you got to look in. You go, well, I've got 3, or I've got 10, or I've got 100. You're still pretty low data density. So if we did it electrically, we're going to put a trench at the top of the ground, and you're out of your PVC, you'd have a cable. And so I can watch the groundwater electrically. So I can't get you a direct water level measurement. I can't get you a direct chemical sample. I can't get you microbes. I can see them. I can see measures of those things, but I can't get you a direct sample. But I can watch temporal changes, and there's a couple of useful things about that. One is I can see where the ground's actually changing. Where's the flow path that's changing with time that I can go, hey, we really need a well right here. This is the spot that's super interesting out of this entire 1,000 foot of our site. Here's the spot that's super interesting. Let's put a well there. But the other thing I could do is tell you that nothing's happening. And so if you've got a site that's been around for a really, really long time, a lot of the times you're like, oh, we got 100 wells. I need to go figure out what's going on because they want to know what's happening now. We haven't really looked at the site in 5 years, but we really need to get some answers. And so you start digging around and trying to figure out where have things not changed or where have things changed. And that's the not changed one is a somewhat harder question to answer, but electrically it's really hard to hide. If I'm going to get repeatable electrical measurements over time, even over years, it's really hard to hide whether nothing changed. So super useful for nothing as well as something. On the problematic side, I get rid of all the problems of wells. I don't get it any cheaper. Doing work out in the environment, doing electrical work and looking around is still a $100,000 kind of thing. And you've got people going out and sampling cables, but I don't have to abandon it. If you walked away, you'd leave a cable in the ground and you'd leave a stick up that got mowed over some point or somebody drove over later. But there's no sort of problem with contaminants migrating because there's a trench up at the surface. In terms of how we look around, so the simple measurement is 4 electrodes, but normally I don't talk about this, but for today it's kind of useful. That measurement is a Wheatstone bridge circuit. That circuit, if you go in the lab as an undergrad in physics, which I did back way long time ago, you can measure precision and accuracy with that thing and find out that you can get the resistivity of a piece of wire to 8 decimal places. And when I was an undergrad, I had no idea why you would measure a piece of wire's resistivity to 8 decimal places. But I went outside later and figured out, oh, this could be pretty handy if I'm going to measure something about the Earth. So you've got a circuit that is super sensitive to changes in electrical property, and you can then spread out the AB electrodes and send current deeper and deeper into the Earth. And the longest I've ever seen was over 1,000 kilometers. So you're not limited by the physics, you're limited by logistics. And then M and N are, hey, we're going to measure some potentials and figure out what's the voltage between those 2 points, and figure out those potential differences. And then we're going to use that to map. So so when we do that, the limits on that are we've got a really good circuit, and back in the 80s we were doing electrical drilling and did that since the 1800s. And so you could take individual data points, and if you could do that, you get about 80 data points a day. So you're somewhat limited there in getting lots of information. You could get some information and you could do things like look for a saline water table or something. In the 90s, we said, oh, well, what if we put all the electrodes in the ground and just let the computer do this? And so then you could start filling in data fields. And what that allows you to do is think about, okay, what's happening over an image worth of the subsurface instead of just a line. And you learn a lot of things about the subsurface being more complicated than you would like it to be. The point of this talk is I can do that again. So as well as having the computer take a lot of measurements, which takes some time, if I just put the cable there, I can hook back up, take all the same measurements again and get how the ground changed since the last time I looked. So if we look at an example here, this was a Sandy DOD site from Nebraska. And what we're looking at is a silt with all the colored stuff is a sand underneath that. The wells said this is pretty homogeneous stuff. The electrical data said, not so much. There's these really resistive patches and then there's these conductive patches in there. And it's not all the same stuff. But they said, well, it looks pretty homogeneous. Let's inject into this well and see what happens. And predicting a priori what would happen, not super simple, but I've got a trace of where the temporal saw it. So we're going to look at the temporal. Now this one, all this variability over here goes to nothing's really going on. And so you go, okay, well, that's not interesting, but we injected over here. This is where it should be interesting. And you see, oh, it got really conductive up in the Vados zone. Water table sitting here about 50 feet. You go, oh, well, when we injected, a lot of it must have shot upward. And we saw that on a number of different data sets, and it was quite clear. But then instead of going horizontally through the aquifer at the screen interval, it dropped down. And we found it about 70 days later. This was a permanganate injection, came out about 20 feet below the bottom of the wells in a sand stringer down there. And it's basically, it's following this, and it doesn't want to go into this thing, but there's very little heterogeneity. There's just enough to make the flow lines bend around. So the temporal says basically almost a very different story from the regular ERI, and taking the single picture, the temporal says where things are going on. So really useful way to see things like fluid movement. If I want to put one of those in the ground, we've been thinking about that design. We've got those in the ground in a few places now, and we've been modifying the design over time. But it's thinking about how do we put in a well properly, but it's instead of being a well to sample water, we're going to sample electrical. Or you can call it a temporal ERI cable or a Terry cable. What you're going to do is trench it in, and you're going to put in grounding grout like they do for lightning rods on a building or a grounding rod on a building. Put some grounding grout around it to make sure that it connects to the subsurface, and then bury it in there and put a cap on there if you want to be set up at land surface or you have a stick up. You're basically thinking about it like I'm putting in a monitoring well, except for you never went below a couple of feet. That width could be 10 meters for looking a couple meters down. It could be a kilometer wide and look down a couple 100 meters. So it just depends on what your imaging objective is. If you're only going out once in a while, you could put the stakes in and come back and put the stakes in if you know where they're at. That's noisy. And what your goal in doing temporal work is you want to get that noise as low as possible, because then you have as much data as possible that is about the subsurface versus being about how you connect it to the subsurface. So we tend not to want to do that. We've done that a couple times for sites that were interesting and deep, and that we could go back and look again, and we can watch. We use that for watching microbes grow. They show up pretty easily on that, but in that case, noisy pictures aren't a big problem. If you're only going out a couple times and you say, well, I don't want to buy a cable, you can put stakes in the ground and put a cap on them, and then that'll allow you to come back and hook up again and take another picture without installing a cable. And so with urban logistics and things, sometimes that's the best call. And for like injections, sometimes that's a really good call. But if you wanted to watch and monitor an aquifer, or you're going to be there for a long time, trenching it in, putting in the cable and putting a well, ends up being the most economical thing to do. And, that cable's, something like a 5 to 10K kind of thing, depending on size and setup. But you're thinking about the cost of installing a monitoring well. Instead, you're going to install a monitoring cable. So they're similar in cost and that sort of thing, except you don't need a drill rig, you just need a trencher or a real serious bunch of students with some shovels. So if we want to look at small changes, we were thinking about what's small look like. And so we took and stuck a 3/8" metal rod in the ground. And this is a soil experiment. So this is tiny. This is the 10-meter scale. And you get a 1.5% change from sticking a metal rod in the ground over a 10-meter domain. If you go and take electrical measurements on the top of that, you can see that happened, but it's tiny as a signal. And so when we later on use the same hole, we dumped about 20 liters of water in there, you get a stronger signal. You get, about 8% signal. And so you can make the signal go higher if you've got a little more space and you've got a nice conductor like water getting the soil wet. But I wanted to leave this here and show you, okay, well, we also got signal just as strong as that metal rod. We didn't do anything out here. And what that is the ground heated up. And so it's a sunny day and the ground heats up and it changes electrical properties shallow. So you've got other things that can go on there in terms of changing electrical properties that if you're doing short-term experiments, you have pretty good control of where you injected or where you stuck something in. But if you're doing long-term, you got to think about seasonal aspects and rainfall and all that sort of stuff. So there's things to think about when you start reading these pictures, and you got to think about how you set up the experiment for getting the changes you want to see. So here's a little longer scale. So now we're looking at sort of the 100-meter scale, and we're looking at a fault zone. And this is a sandstone siltstone sequence. And in the fault zone, there's this clay that develops. This a pseudokarst area where you've weathered away and made a clay bed inside of the fault zone. So we can interpret some geologic things and maybe see that the sandstone's a little deeper here, or there's been some collapse into the siltstone maybe, and that it's a little bit different geology. But when you say, well, where's the flow? And you go, well, sandstone's got good flow. Siltstone's lower hydraulic conductivity. We can core through that and make that call. But I've got a couple bedding planes listed there in the dashes. And if you core through this, there's a couple of bedding planes there. And when you go to temporal information, when we looked at lower bedding plane is actually the most active flow zone in this system. You can see up here where the water table's changing that the water table has gone down and dried out. And so we have some resistors showing up in the water table domain. But for the flow zone where water's going through, it's that bedding plane that really is controlling where things are at, except for where the clay plug is at. It kind of prevents stuff from flowing along that bedding plane. But that temporal shows you where the groundwater is flowing. Instead of going through an analysis and trying to figure out where's flow at, you know that your best flow point is probably right here. And so you can stick in a well and get the spot where most of the flow is happening, get the high flux region. Unless you don't want the high flux region and you're wanting to see maybe where contaminants got buried somewhere, and you go look in that clay for where the contaminants diffused in or something. But you're looking at the hydro in an electrical way instead of looking at it in a, I'm going to integrate these well data and integrate this geology information from the logs and figure out what's going on. You're going to integrate a set of data that says, where did the ground change a lot and what did that mean? So another one that you want to start thinking about is this is an injection. This was a vertebra injection system. So we had several injection intervals, and scientifically it'd be nice to inject into each one and separately image each change, but this is a before and after with injecting into all of them, and then deciding if the remediation strategy worked well and if we got enough coverage. But you get some weird things and we get more conductive, and that's really clear up here in the Vados zone. It got more conductive, and that makes sense. You made it wet from injectate, and you can see that you basically made the whole Vados zone wetter over this big interval. But below the water table, you get resistors and conductors, and it's a brackish groundwater. So it might get more resisted because you injected injectate that was fresher, or the other thing we see in some of our injection imaging that there's actually precipitation going on, and part of the plan was to make precipitates, and usually like a manganese oxide or something. But so you get lots of signals, and so you've got to think about how to set it up that you don't get too many signals. And a lot of times in groundwater, we're like struggling to get enough data. When you do these things, the changes can be so dramatic that you start going, I'd really like less data to be able to control my interpretation. And so it's something you've got to consider as you go through what's going up, what's going down, and where it's happening in space. Are you taking enough pictures to get what you need, or do you need to take more pictures? More pictures don't necessarily help. Sometimes you get so much data that you get quite lost, but these are things to think about when designing if you're thinking about designing where to put wells, you're thinking about where designing to put images and how often to collect the data. So I do a lot of analogies to photography. I also do a lot of dog photos, so that's just the way it works. But shutter speed, how fast can you look? Sort of hourly, you know, so shutter speed on a camera, I'm gonna watch somebody coming across the finish line in the Olympics. Yeah, you're not gonna do that. You're gonna do things that are changing hourly, but groundwater systems, there's a lot of things you can do that are much longer than hourly scale. Your resolution is meter scale, so I can see a metal rod, but you're not thinking about seeing super tiny things. You're seeing about how it influences things and about the meter scale or larger. In terms of developing it, within hours, you can get things developed and you get your pictures back. Interpretation sometimes is longer. Sometimes you pick it up and you go, oh, that's where it injected to, good. And sometimes you go, why did that happen? And you got to think about what that meant electrically and why the subsurface did that in that location. Was it a reaction? Did something else happen that you weren't expecting? And so depending on how you set up your experiment and what you're trying to see, sometimes that's quick, sometimes that's slow. And then dimensions, you can look down a couple meters, you can look down a couple 100 meters. The physics isn't limited, but for our industry, that's a pretty good range of looking around at things. After doing this kind of work in a number of different sites, either academically or commercially, it's not a problem of getting data or signal. You can get signals back and you can see things. It's managing the data and managing all the information you're collecting and trying to pin that down in an effective way. You can collect more than you can digest. So low data density has its own issues. High data density, you've got to manage that if you've got a fire hose of data coming at you. When you go to take images, there's the angle and the setup relative to structures in the subsurface that you want to think about how you're going to cut across there and watch the changes so that you get the results that you need to get the answers you want. You're looking two-dimensionally, which is way more powerful than a single well, but you still have a lot of interesting things relative to your angle, relative to flow lines and different features. So thinking about setup is real important, and it's not obvious in some ways. And then noise level or critical, we've gotten down to 0.5%, which is more research scale than you're normally going to get. But you definitely need below 30%, and then you prefer if you can get down below 3%, which is not easy to do, but you can do that if you've got some setups for that. Especially with keeping your electrodes in place. You can really see a lot of detail in the subsurface that's purely subsurface changes. And so keeping track of those things, it's a little bit different ball game, but it's quite powerful for us to understand how aquifers are functioning or how our remediation strategies are working. So in the future, we're doing work on injection or think about doing like thermal remediation monitoring and watching what's happening as you're monitoring things that we're trying to do to the subsurface. But long-term, site monitoring, it's just like thinking I'm going to put out a monitoring well and I'm going to watch it for the next 20 years or however long we're thinking on either a water management strategy or on a remedial strategy. But instead of having a 2-inch window in the subsurface, you got 1,000 foot or you got 1 kilometer or you got however much you want to look at as a panel in the subsurface instead of just a little bit. So instead of just looking for the interesting spot, you could also have data that supports that this part isn't interesting and us spending money and time in this part, there's nothing going on in the groundwater over there. It's been stagnant, and we took a picture 6 months ago and the picture was identical. And so there's been no change electrically. It's unlikely the fluids are doing something interesting there. So in terms of a sampling interval, I'm not sure if people use this more to say, here's the interesting spot, or if they'll use it more to say, here's definitely not interesting. We don't have to go mess around there other than sampling that cable every once in a while. But so there'll be some sort of an interval where sampling it occasionally will be useful on a management strategy. But I don't know if that's going to be quarterly or other, depending on how people use the tool. So questions?
Hey, Todd. Yeah, we've got a couple of questions that have come in through the talk. First one is from a Carla. Try the last name here, Brasamile. Her question is, does this technology work under buildings that may have embedded electrical conduit to power high voltage machines used for manufacturing?
So we've gone through on a single image basis through a lot of buildings now. The only thing that really kind of gets us if they put in a grounding grid. So like around transformers where you, instead of putting in a couple of electrodes to ground the thing, they basically put in a metal mesh under the ground. And that gets really hard to see through because essentially I can't get my current to not just flow right underneath the building. But what you could do is set up a single image. Hey, yep, that worked great. Okay. And then a decision of, well, do we just install those electrodes permanently through the building and hook a cable up once in a while, which has its pluses and minuses for financial and for logistics if it's an active building, or, yep, okay, let's just trench in here, manage we don't hit any things, and or put some way to get the cable in permanently near some place where you wouldn't walk on it, but some way to get that installed permanently that, okay, we can watch the building forever now. I had a client that they just built a building over one of his old sites and they thought they were clean and now the wells came back hot. They had the back diffusion issue and they got to go back in and clean, but now they got a brand new building somebody else owns. And so it'd be great on those sorts of situations of, yep, we're going to declare it clean, but we're nervous enough. Let's just spend let's spend enough to put in a couple cables, build a new building, and we already have a monitoring system under the whole thing that if things go bad later, I don't have to abandon it, but if I need it, I can go plug into the side of the building and take a picture. So whether that's for I'm going to install a new gas station or whether that's I'm going to install a new factory and I'm worried about an old contaminated site, it's a great sort of way that I've always thought to be proactive and say, okay, well, in case something happens, I don't want to have to dig around this building. Let me just get pictures now, get a background picture. And then if you ever have a problem, just go plug back into that cable and take a look again. And you've already got a subsurface monitoring system under the building.
Great. Next question is from Keith Rapp. He asks, was your fluid surfacing caused by, sorry, this is in reference to slide 13. We want to hop back to that guy. And his question is, was your fluid surfacing caused by the potential fracture flow or the deviation points in the vertebrae well?
That's a great question. And so I actually just installed a vertebra well at the university, and we're going to be playing with it. For that real conductive spot, that they drilled it afterwards and it was confirmed to be really fractured and full of fluid. But was that because the drill bent, or was that part of the fracture system? When they drilled into it, they said they hadn't seen a spot come back on drilling like that before. So, we're interested in whether when you're doing the horizontal, when you bend like that, and, it doesn't take a lot for the rig to do that. It's quite happy to do that. But does the rock get kind of crushed as those pipes are going by and cause a fracture location that might influence the way these things? So the guys from Vertebra and the horizontal guys are interested in these problems. So we've now got a research well like this that we're going to be playing with some of these issues and testing these issues. But a lot of the surfacing was associated with the fractures we could see and the flow zones we could see, and the little green things up at the top are where the fluids did surface on this injection. And all the injections we imaged, stuff always goes up and down by a lot more than people think. So, but there's a lot going on, and these images you start going, oh, I got new questions now, and so we're starting to answer those on a research basis too.
Awesome. Next question is from Dennis Lowe, and his question is, can you use this for looking at PFAS?
So we've looked at PFAS from an electrical perspective. So PFAS as a chemical is really, really resistive, but they make it into a foam film, which is really quite conductive. And then it's really, really soluble. So we've been looking for a site to tell you what that looks like, but we haven't got, I looked at one site where they were pretty sure it was clean and it had a little bit of conductance, but not enough to be super interesting. But it'll show you for PFAS, a lot of it I think is going to come down to just finding the flux zones, and that's going to be the main thing to treat. And so using it on a temporal basis and defining where the flux is so that you can treat the flux zones where almost all the mass is coming, would be a way cheaper option than trying to use wells and find those areas and trying to treat it in some sort of a bulk way. Being able to separate where high flux is versus no flux, I think is the way that you could do PFAS economically. So I don't know if it'll ever be a direct detection of PFAS itself. I think it'll be through being able to define the flux zones that you can treat the mass and define that you've treated the mass flow location versus trying to treat it in some traditional manner.
Great. Next question from Chris Bonds. He says, fascinating talk, Todd. How can this technique be integrated or synergized with airborne electromagnetic surveys? For context, California Department of Water Resources is surveying dozens or more of groundwater basins / subbasins over the next 3 to 5 years as part of a SGMA implementation.
Yeah, and I love California for doing that. I've been trying to get folks around different places to do that because it's going to be really quite helpful. So we've got that in Oklahoma. So we've got a research aquifer we use called the Arbuckle-Simpson. We work with the EPA ADA lab, the groundwater lab for the EPA, and we've got a research site there. But we've had helicopter electromagnetic, and then we've had this kind of work done on top of that. So what you do with that is you look at the helicopter data and you say, okay, I can see that there's some feature running through here, but you don't have, you got a notion of like maybe you got a fault zone or something, and you can kind of see there's something there, but there's a lower resolution than this kind of work. So you basically have a little bit fuzzier picture that you go, yeah, that spot in the county looks really interesting and might be something controlling this issue. And so what you do is then you go ground-based with this, and you go across those features and you resolve it. So you'll see, okay, we got a conductor on the HEM showing up as a couple of giant pixels, and now we've imaged it, and that's actually a fault zone with sort of 3 dominant fractures running through there. And you can start picking off what's going on and looking at that relative to targeting that area. So they're both electrical hydrogeology. One is just at a helicopter scale, and then one's at a ground scale with a higher resolution that you can pick off things and play with the temporal. It's hard to do the helicopter temporally, but that database across California is going to be awesome because that basically sets the electrical framework to look at this. You then take this ground base and you basically clear up the edges of things and find out what the real features are. And then you can monitor that temporally to manage aquifers, because you're going to start managing it like you're managing rivers. So you're going to be looking at fault zones that are controlling flow between aquifers or controlling flow between basins, and you're going to be keeping track of those because you can now, and you can watch what's going on there and monitor what you need to, but you're going to be doing it like you're looking at the surface.
Yeah, great answer. Very interesting topic. Next question is from a Michael Bister, and his question is, what constituents does this technology detect best?
So if you're a chemist, you go, okay, well, you got to be an electrochemist, and it's, did that change the EC of the fluid at all? And so if you've got, like, you went from 110 microsiemens per centimeter to 125, I probably could see that. And so, you don't need a big change in EC to be able to detect it. You're testing bulk changes here, and there you're testing just fluid changes. But if you change it by a few microsiemens per centimeter, that becomes detectable. In terms of trying to use that for management, like when we think about injectate, we go, okay, well, should we keep it fresher, add a little bit of salt? And you're not adding salt to make it into a brine. You're just trying to tilt the EC one way or the other to make it a little more visible in the injection. This is similar to the doctor's going to go put injectate into you and watch an image, what your gallbladder is doing or something, and they add a little bit of something to make the image show up a little more. For us, that's a little bit of sodium chloride, or making sure you don't add a little bit of sodium chloride if you want it to go more resistive. So you're playing that game. The other game you got to keep track of is my chemistry when I inject it, is that going to cause a chemical reaction in the aquifer that's an electrical change? And so, if you're precipitating something, you're gonna make it more resistive. If you cause a chemical change where ions are released, that makes it more conductive. And so there's gonna be times where you inject and you go, what the heck just happened? It went the wrong way. And for people, they're like, okay, yeah, it changed electrically, it's supposed to. And it's like, no, it went the wrong way. What reaction really went on? So it's just thinking about all your chemistry relative to what that does electrically, which is it's a different way of making your brain work with chemistry.
Very good. Another great question here from Tony Winkle. His question is there a large-scale application of this technology? The MWA has a 5,000 square mile service area with 36 distinct groundwater basins, and not nearly enough monitoring wells.
Well, it's basically you're saying roughly $10,000 gets you, 1,000 feet to a kilometer worth kind of things, that kind of scale of investment, and then you got to trench it. But you're talking about, well, how big are my cables and where am I going to stick them efficiently, instead of thinking I'm going to get a well that gets me 2 inches or 6 inches worth of aquifer location. You're doing panels where you're doing, okay, I needed to go big, so let me do a kilometer here and look at the aquifer flowing through this kilometer, and you can then daisy chain cables up and make big giant panels. But it just depends on, you're essentially going to large scale and you're going, okay, where would a well be handy? Okay, that told me about 2 inches of this thing. Well, you just say, okay, well, instead of 2 inches, I'm going to think about 1,000 feet, or I'm going to think about a kilometer worth, or let me panel this thing for 3 miles because that's super helpful for my water district, or what problem I'm trying to solve, that I can demonstrate that nothing crossed through this 3 miles. It's not my problem, it's your problem, or vice versa on the legal and political sides.
And then we have another question from Michael Pfister. What are the depth limitations?
It's the logistics of how long you could put a straight wire in the subsurface somewhere at the trench. So, we've done down to 1,000 feet and looked around, and we've drilled contaminant targets to 700 plus feet, finding the contaminants in the targets. So you're not limited by the logistics of the method. You're limited by the logistics of what's too long of a cable, or what's hard to install, or in this urban area, are we going to run into a house or a building that we're not allowed to go through? So it's more logistics limited than technique limited.
Yep, great. Another question from Chris Bonds here. How does this technique perform in alluvial basins versus fractured rock areas?
So we've done this in anything from a salt pan, which is basically the most conductive thing you can do on Earth, is you're just looking at straight salt for the entire image, and the whole image is less than like 1 ohmmeter worth of conductance. And then we've looked at dry granite. And so about as resistive as you're ever going to get. And we can get good data sets and results from both of those. And so we've done all sorts of different kinds of geology over the last 20 years, and we haven't found a place that is hard except for transformer yards with grounding grids. It's no matter how well I play with the signal, I can't get it to go past that grounding grid. But otherwise, geology is not a limit. And so actually, Kyle did a project looking at alluvial where the alluvial model wasn't working. And as a fine grain alluvial aquifer that didn't fit the model, he did imaging, and there was something at the bottom of the aquifer, so he did bigger imaging, and there's actually a paleo channel that was much narrower but much coarser, and so you had this big gravel tube sitting underneath all this fines controlling the hydro that nobody ever noticed, and so the model wasn't working, and the imaging explained why quite easily.
Great. Well, that's it for questions. So unless anybody else has any questions, I think we can go ahead and call that a wrap. Todd, thanks so much for the talk and the great Q&A. And with that, I think we'll close the meeting.
Well, thanks for everybody's time. And if you got questions, just give me a holler.
Thanks, Todd.